Hello everybody and welcome to Electric Fields Lesson 4. Now today's lesson is going to be slightly different from previously. In today's lesson we're going to be focusing on some of the mathematical skills and approaches that you need to make sure that you understand and can apply when it comes to especially exam paper questions and things like that. Firstly though, let's just remind ourselves as usual of what we did last time. Firstly, we looked at electric potential energy and we came up with the equation EP for electric potential energy is equal to Q1 Q2 over 4 pi epsilon naught R. We then looked at electric potential, and the definition for electric potential is there on the screen for you. The electric potential at a point in an electric field is the work done per unit charge in moving a small positive test charge from infinity to that point. Now to put that into an equation, we had V is equal to Q over 4 pi epsilon naught R. Now one of the key points that we made last lesson is that both of these quantities, electric potential energy and electric potential, are both scalar quantities, and it's one of the things we're going to be looking at today, exactly how we need to treat scalars and vectors differently when we're looking at it from a mathematical point of view. So on to today's lesson then. What you can see on the screen is a past paper question from AQA. It's actually from January 2004, which I know is a long time ago, but one of the beauties of physics is that the physics itself doesn't change. The style of questions may be tweaked over the years by the exam boards, but at least the equations and everything that we're trying to study remains exactly the same. So if you have a quick look, two charges P and Q are 100 millimeters apart. X is a point on the line between P and Q. If the potential at X is 0 volts, what is the distance from P to X? And you can see this was a multiple choice question, and we'll work out which one of those is the correct answer. What we're also going to do, just to show you a difference in our mathematical approach, is we are going to also work out what the electric field strength at that point is, once we've determined exactly where this point X is going to be. Now as usual, and what we will always say to you is whenever you get a question like this, you must always draw a diagram. Fortunately the diagram is given to us and we can draw onto the diagram just to help us to see exactly what's going on. So on the line in between, I'm going to put a point here and I'm going to label that X, and that's the point that the question is talking about. I'm also going to draw a distance there and I'm going to label that little x, and it's that distance, little x, that the question is asking us to calculate. By looking at the diagram, we do have another distance on. It's the distance from X to the -6 microcoulomb charge. Now that as a distance will be 100 millimeters minus X, the distance that we're trying to work out. Now some of you may be wondering why I've written it as 100 minus X and left it in millimeters rather than writing it as 0.1 minus X and converting it into meters, but I'll explain in a moment exactly why I've done that. Now we're told that at X our potential is 0. So that gives us a very big clue as to what we've got to do in this equation and in this question. Just to clarify and make sure that we know what we're doing, I'm going to label the +4 microcoulomb charge as Q1. I'm going to label the -6 microcoulomb charge as Q2. Each of those charges will give us a potential at that point X. They will give us V1, that's going to be the potential from Q1, from the +4 microcoulomb charge, and it's going to give us the potential V2, which is from the -6 microcoulomb charge Q2 as we've labelled it. Now because we're dealing with scalars here, whenever we're totaling scalars up, we just add the numbers together. So the total potential at that point will be V1 plus V2. But we also know that that is equal to 0 from the question. We can now start to form ourselves an equation. V1, well, let's just remind ourselves of the equation for V first. V is equal to Q over 4 pi epsilon naught R. So let's start writing this into an equation. V1 will be Q1, that's the plus 4 microcoulomb charge, divided by 4 pi epsilon naught, and our distance will be x that we've drawn on the diagram. To that we will add Q2 over 4 pi epsilon naught 100 minus x. And once again we know that that total is equal to 0 because that's what it tells us in the question. Straight away we can start to algebraically manipulate this. Now here's the first key mathematical point that we need to make sure we understand. It will be far better and far easier for you to approach questions from an algebraic manipulation point first before you start to really plug numbers into the equations. From the equation we've written, I'm going to subtract the second term. So the term for Q2, I'm going to subtract that from both sides. What we're left with then is Q1 over 4 pi epsilon naught x is equal to minus, because we subtracted from both sides, Q2 over 4 pi epsilon naught 100 minus x. That's our distance. The next thing we can do, and this is again one of the advantages of doing the algebraic manipulation first, we can see that on both sides of the equation, on the bottom we have 4 pi epsilon naught. They will therefore cancel out with each other. That's immediately got rid of a load of constants that would have got in the way of our calculations, and immediately it's going to make everything look a little bit nicer. We can start to plug some numbers in then. For Q1 we have plus 4 times 10 to the minus 6 coulombs, and that is divided by x. That will equal minus, Q2 is minus 6 times 10 to the minus 6 coulombs, and we will divide that by the distance, 100 minus x. Now again at this point we can see some things are going to cancel out. The 10 to the minus 6 on each side of the equation will cancel out. We also have minus and minus on this side of our equation, and therefore two minuses make a plus. Those two will end up cancelling each other out. We can also see that any conversion that we would have done in order to change x, in order to convert x from millimetres into metres, will also cancel out. If I write it in green, we can see that what we would have done is multiply by 10 to the minus 3 to convert it into metres on that side. But we also would have multiplied by 10 to the minus 3 to do metres on the right hand side. And again, those conversion factors end up cancelling each other out. What we're left with is 4 over x is equal to 6 over 100 minus x. And I'll just leave that in brackets for a moment. So to move on to a fresh slide then, because I was running out of space on the other one, we left the last slide with 4 over x is equal to 6 over 100 minus x. Now that at that point should hopefully be quite easy for you to solve. We will cross multiply, so multiply both sides by x and multiply both sides by 100 minus x, and we're left with 4 brackets 100 minus x is equal to 6x, and this is dead easy now, so we'll just follow it through anyway. 400 minus 4x, multiplying those brackets out, is equal to 6x. If we add 4x to both sides, 400 is equal to 10x, and what we're left with is the answer of x is equal to 40 millimetres. There's the answer. The answer is A, 40 millimetres. So just to remind you, when we're looking at scalars, we simply calculate the value, no matter how many there might be, at a particular point, and then we just add them all together. Because they're scalars, we don't need to take account of the direction in any way, shape or form. What we'll move on to next then is to look at how our approach needs to be different when we're dealing with vectors. And earlier on we said that once we'd found where this point x is, and just label that on as 40 millimetres. Once we'd found that point x, we want to know what is the electric field strength at that point. First thing that we need to remember is the definition for electric field strength, and electric field strength is the force per unit charge on a small positive test charge. That gives us the excuse then to go ahead and put a small positive test charge at that point, and then to think about exactly what's going to happen to that small positive test charge. From Q1, let's just relabel these in Q1 and Q2. From Q1 then, because we've got two positives, we know that we're going to have a repulsive force, and that force is acting in that direction. It's acting to the right, the way that we've drawn it on the diagram. The second one, so from the -6, the -6 microcoulomb charge, will also be an attractive force, a force acting to the right, E2, because they are opposite charges and opposite charges attract. On the board then we can see that we've got a force diagram. We've got E1 and we've got E2. Really they're not forces, they're electric field strengths, but they're vectors nonetheless. In order to calculate the total electric field strength, we must therefore add E1 and E2, but we're only going to add the magnitudes of them, because we know that they're acting in the same direction. We can therefore straight away start to plug some numbers in. For electric field strength, we've got the equation E is equal to Q over 4 pi epsilon naught r squared, and note we are squaring the distance here, not just having over r. E1 then comes from our 4 microcoulomb charge, so 4 times 10 to the -6 divided by 4 pi epsilon naught multiplied by the distance, which is 0.04 squared. Now, I have converted to metres here. Why have I converted to metres? Well, mainly from experience, I know that I'm not going to be able to cancel anything out here, because we're not equating anything to zero. We're simply trying to find what the total is. So unfortunately, in order to make sure that we get our units correct, I do need to convert into metres here. I will add to that 6 times 10 to the -6 divided by 4 pi epsilon naught multiplied by the distance is 60 millimetres, 0.06 squared. Now you'll notice that I've dropped the minus sign from what we've labelled as Q2, and that's because we are only interested in the magnitudes. We're only interested in the magnitudes coming back to the diagram and the directions that we initially drew E1 and E2 in. Now, once you feed that through your calculator, I'm not going to patronise you and sit and write everything out with epsilon naught in there. But once we've done that, we will get the answer of 3.75 times 10 to the 7 newtons per coulomb. As a direction, that electric field strength will be acting to the right. The positive is therefore implied in the question or in the answer. What we can see then is that if we have two oppositely charged particles, two opposite charges, in between we will get a point where the net potential, the total potential, is zero, but at that point we will still have an electric field. Now, to put a slight difference on this question, I'm going to replace the minus 6 microcoulomb charge with a plus 6 microcoulomb charge, and we'll see what difference that makes to our question. We're going to take exactly the same point, which was 40 millimeters from P, and therefore 60 millimeters from Q, and we will work out what the electric field strength at that point is, and we will work out what the electric potential at that point is. Firstly then, electric field strength. Straight away I will place a small positive test charge at that point. I like putting a small positive test charge there because I find it far easier to visualise the situation, visualise the problem, if I can think of it in terms of force rather than in terms of electric field strength, but knowing full well that from the definition of electric field strength, the small positive test charge will end up disappearing anyway. I'll relabel the plus 4 microcoulomb charge as Q1 and the plus 6 microcoulomb charge as Q2. The first direction for electric field strength E1 will still be acting to the right. We've got two positive charges, therefore it is a repulsive force, and that will act to the right. We've also though now got a repulsive force from Q2. Because we've changed it to a positive charge, that is now a repulsive force, and that will therefore mean that the electric field strength will act to the left. Because we're dealing with vectors here, E2 is now in the negative direction. When we calculate the total electric field strength, we've now got to take E1 and subtract E2. We subtract E2 because it's pointing in the opposite direction. Immediately we can now plug numbers in. 4 times 10 to the minus 6 divided by 4 pi epsilon naught multiplied by 0.04 squared, and remember to square it because we're dealing with electric field strength, and we will subtract from that 6 times 10 to the minus 6 divided by 4 pi epsilon naught 0.06 squared. The answer to this therefore becomes 7.50 times 10 to the 6 newtons per coulomb. Because again we've got a positive value, we know that the net electric field is acting to the right. For the potential V1, V2, again we simply add the values together, so our total potential will be 4 times 10 to the minus 6 divided by 4 pi epsilon naught multiplied by the distance 0.04, and again from the equation we're not squaring the distance here, we will add to that 6 times 10 to the minus 6 divided by 4 pi epsilon naught multiplied by 0.06. Once we've put that all into the calculator, what we're left with is an answer of 1.80 times 10 to the 6 volts, or I would prefer to write that as 1.80 megavolts. So that's it for this lesson. We won't worry about an example today because we've obviously done quite a lot of mathematical content in this lesson. Just remember then, we've got to make sure we understand the difference between how we deal with scalars and vectors mathematically. Whenever we add scalars together, we just take the values and we add those values together. Whenever we're dealing with vectors, we must ensure that we understand the direction in which they're acting first and then add or subtract as necessary. That's all for today. Once again, any questions, please get in contact with me. I hope you got something useful out of that lesson. It will obviously be extremely important to you when you come to past papers, and obviously even more important when you come to exams, that we get these mathematical skills embedded in what we do and we understand exactly how we should treat and how we should approach different problems depending on whether we're dealing with scalars or with vectors. I'll see you next lesson.